So, in the last lecture, we covered rocks that introduced the course to rocks, in which there are three main types of rock: igneous, metamorphic, and sedimentary. And in the last lecture, we covered igneous rocks. In this lecture, we should cover metamorphic and sedimentary rocks. Now, sedimentary rocks can be divided into two types. There's the mechanical, or detrital, or clastic type, and the chemical, or biogenic, or precipitate type. Now, chemical sedimentary rocks can be biogenic or precipitate, whereas mechanical rocks are detrital and clastic all at the same time, which might be a bit confusing. So in this rather cute little graphic here, you can see how the mechanical or detrital sediments will start off possibly up here as little bits being weathered out of rock and slowly go down, being brought down by gravity and water, and be redistributed perhaps by the wind, by beaches, by waves, and eventually go down possibly to the sea and to the deep abyss. As it goes down, more or less, it sort of gets like there are big bits up here and little bits here and really teeny tiny bits down here that form the detritus of the detrital or mechanical sedimentary rocks. Whereas the chemical are usually either precipitated, like in evaporitic deposits here, precipitated out of water from evaporation of water, or they will be from biogenic, the bio being life, born of life. And so live things actually should be deathogenic because it's actually born of things dying and leaving their bodies strewn around the floor of the ocean. So let's go through these in a bit more detail. Mechanical, detrital, clastic. These are mostly divided by the size of the little fragments of detritus. Really big bits are often called conglomerates, or grit, or gravel, or rudite, or breccia. Slightly smaller are called sandstone, or arenite. Then there will be siltstone, which are even finer, and shale, which is possibly a bit finer, and wacky, which I mostly have on here because I'm kind of amused by the idea that there's a rock type called wacky. It used to be called grey wacky, but for some reason people just decided to call it wacky. Then there's the chemical sedimentary rocks, which will include things like limestone and chert, and also phosphatoid. So there are a number of authorities on grain sizes. There is a recently decided international grain size authority, which is quite useful because it's quite simple. Anything above 2 millimeters, this is all in millimeters, is not sand. Okay, so fine gravel, medium gravel, coarse gravel, cobbles, boulders, large boulders are all bigger than 2 millimeters. Anything less than 2 millimeters, down to 0.02 millimeters, is sand. So 2 millimeters to 0.02 millimeters is sand. Below that is silt, and even finer at 0.002 millimeters across is clay, or at least clay-sized particles, because not all clay-sized particles are actually made of clay. So, clastics. Rudites are from the Latin rudus, which means crushed stone, debris, or rubble. Conglomerate is just it's coming together to agglomerate. Breccia is angular bits. That's an Italian word, breccia. Here we have a angular bit and a breccia. Here we have a rounded bit and a conglomerate. Grit or grit stone is just slightly coarser than a sandstone, made with very coarse sand that is very good for making millstones with, things like that. Gravel is things like this conglomerate, which was once gravel, but then it's been cemented together. Here is an example of a breccia. You can see it's got these angular lumps in it, and it's been cemented together with calcite. So, sandstones are a type of clastic. As it said, if you use the International Grain Size Scale, things between 0.02 to 2 millimeters would be classified as a sandstone, also sometimes called arenites. They're called arenites because of arenas. This is an arena, and on the floor of the arena was sand. And so you have the sand in order to soak up the blood, and you just brush it up and it makes it nice and flat again. So there's a number of types of arenites or sandstones. This is known as a lith arenite because it's got little bits of rock in it. So you probably think that most sandstones, arenites, are made of quartz. There's probably a piece of quartz here. But they aren't always. This sandstone, you can see it shows off the bedding and is quite nice. This one I particularly like. This is probably made with Nubian sandstone. It's from Egypt, and I've met this gentleman personally. And one of the really nice things about him is that the minerals within him in Nubian sandstone are not just quartz but also feldspars. And if you remember from earlier on the lecture about identifying minerals, there's this thing called cleavage, where minerals break, showing a flat surface, and feldspars can do this. They will break, leaving a shiny flat surface. And so if you meet this gentleman personally, you'll see that he sparkles, rather like a vampire in that horrible teenager series that some people liked. I just heard about it, I haven't read it. Another thing I like about this particular gentleman is he's strongly reminiscent of Yul Brynner in The Ten Commandments, which is one of my all-time favorite movies. So argillites, sometimes called lutites, are made somewhat of clay. Argillite is clay. So if you think silt size is less than 0.02 and clay size is about 0.02. So shale, or argillite, is fissile because it has phyllosilicates in it, or actually real clays. Because of the clays, and if you remember phyllosilicates, remember the one type of silicate I asked you to remember? Phyllosilicates are flat. And so when you get a lot of these flat minerals in this rock and you hit it, it'll break into these flat bits, and this is called fissility. As opposed to a mudstone or lutite, which is not fissile because it doesn't have clay in it. It's just filled with silt and clay-sized particles. Now, there's no green arrows coming up on this one because this is kind of complicated. I'm just sort of making you aware of how complicated some of these things can be. So, here we have a ternary diagram. Remember the ternary diagram I showed you in the last lecture? So in this case, up here we have basically silicious resistates, which is basically bits of quartz. Here we have feldspars. And here we have labile fragments, which is things like clays. And the matrix is greater than 10%. So that means things smaller than a sand makes it a wacky. It's like a clayey sandstone, and that's what a wacky is. And you can have a feldspathy wacky, a lithic wacky, and a quartz wacky. So ordinary arenites have a matrix of greater than 10%. No, matrix is less than 10%. Okay, so these are mostly the grains. Now, if they have a lot of feldspars, they're feldspathic arenites. And if they're filled with rocks, they're lithic arenites. And if they're filled with quartz, they're quartz arenites. So wackies contain more than 10% matrix. Aeronites contain less than 10% matrix. Arcos, another word for feldspathic aeronites or feldspathic aeronites, contain less than 50% lithic and less than 10% quartz. So here you can see a thin section of one of these feldspathic aeronites. But as I said, the point of this is just to show you sandstones can be quite complicated, which will do. This, however, is supposedly made of a wackie. Very nice. So this is a geological map of Egypt, and if we zero in on this bit, you can see here we have large flat deposits of limestone, and here we have the green here is large flat deposits of sandstone on top of the basement, which actually looks like this, which is a Precambrian for the most part basement. It's very ancient. Like the shield of Canada, there's a shield under Africa, and on top are flat rocks. So if you ever drive to Hamilton, which, you know, some people do, or to southwest Ontario, you will go past the Niagara Escarpment. Or if you go to Niagara to see the falls, you will see the edge of the Niagara Escarpment. And these are actually very ancient limestones, much older than these limestones of Africa, which are flat because they're sitting on an ancient basement. So this ancient basement here is exposed because of the Red Sea, which create this dome which was eroded away to reveal the underlying basement. And in this basement are all sorts of neat rocks, particularly in the Wadi Hammamat, which is this wadi coming into the Nile, which is here. So in this ornamental stone map of Egypt, you can see here's the Wadi Hammamat here, and you can see all the rock types in it. And this so-called wackie, see here it's still called grey wackie, comes from this area. So what a grey wackie is something which is deposited in a very deep ocean basin. And what happens is that when you have sediment being brought down, perhaps by rivers, every so often there's a surge. Most deposits, most rivers tend to flow and deposit things periodically. It's not like it's continuous. What will happen will be major storms during specific times of the year when a lot of sediment is brought down from the mountains and deposited into the sea. And at that time there'll be these surges called a turbidity current. And these will be deposited, and you have these turbidity currents creating all this murkiness, which eventually will settle out. And what happens when all this sediment settles out is the sandy bits are deposited before the silty bits. See, the heavy things deposit out. This is a very useful approach to making clay-rich deposits when you want to make pottery, because it will take the sand out of your clay. But when it happens in nature, it forms this graded bedding, which, if you look closely at this statue here, is exactly what we see in its shoulder. See the banding there, you see? So, chemical sedimentary rocks include biogenic, which is what we're actually looking at here, and precipitate chemical sedimentary rocks. So biogenic are from things dying, like all these things will die eventually, it's the way of all things, and just fall down to the bottom of the sea and just sit there and turn into a rock eventually. Precipitates are from evaporation of water. So they form by the precipitation of dissolved elements from water during evaporation. Travertine or calcite is deposited like this. This is Egyptian alabaster, of course. Gypsum, or Iraqi alabaster, is precipitated from seawater after about 80% of the water has evaporated. Halite is precipitated from seawater after about 90% of the water has evaporated. This is one of the ways traditionally people have acquired halite, salt, for their diet, is they create these things known as salt pans, where they let seawater into this flat area, then block it off and let it evaporate, and what's left behind is salt. This is a natural precipitate of travertine. You see the calcite is being deposited by water, and it will make Egyptian alabaster like this. You can see where the deposits have accumulated. So this is found in a number of places in Egypt. The area of Asyut and Suez are particularly well known, but this is actually near Helwan, and you can see this is a quarry of alabaster or travertine from this limestone hill. So gypsum, of course, is the well-known Baghdad marble used for Neo-Assyrian sculpture, like this. So there are also siliceous precipitates, and these are related to, again, biogenic origins. You have silica in these organisms, in sponges, and these die and leave their skeletons behind. So in a way it's actually biogenic, but what happens, it turns into this ooze, which sort of accumulates at the bottom of the ocean. This is how you have nodules of things like chert and flint. It doesn't stay behind as little spicules of silica. It conglomerates or precipitates into these oozes, which turn into these useful lumps of chert and flint, which you can then make useful things out of. There's a thin section of flint. So carbonate rocks. Limestone is the best known carbonate rock. Dolostone, made of dolomite, is another type of carbonate rock. This, as you can see, is clearly a biogenic limestone made of the dead organisms of calcareous skeletons which accumulate on the ocean bed. But it may actually be a precipitate, a chemical precipitate of calcite out of the sea and into the seabed. Dolomite is from replacement of calcite with a magnesium-rich mineral known as dolomite. This is basically what this is saying. Chemical replacement of calcium carbonate, which is the pink bits. This has been dyed pink. It isn't naturally pink. With magnesium-rich fluids. I'm going to go back. So this is completely replaced by dolomite. You can see the crystals growing and becoming bigger and bigger. So this, of course, is what things like this are made of. The very nice limestone in Egypt. This is one of the finer types, which you can use for making reliefs. So this is quarried in various places. This is Asyut. And so here you can see these large deposits of limestone, which would be on top of the sandstone, which is in turn on top of the Precambrian basement. So, metamorphic rocks. So metamorphic rocks are rocks which may originally have been sedimentary rocks, or they may have been igneous rocks. But what happens is they get changed through pressure or heat. And so here we have a hypothetical situation with a subduction zone bringing rocks down closer to the core and being metamorphosed by pressure. The further down you go, the greater pressure. Also, the further down you go, the greater heat. But you can also have metamorphism around here. This is a magmatic pluton come in here, and this will be cooking the surrounding country rock, as it's known. And so this will be mostly temperature rather than pressure. This distinction between pressure on this side and temperature is what defines various types of metamorphic rock. Regional metamorphism is pressure and temperature, which is up here, whereas thermal metamorphism is just temperature. And so you'll get this where you get igneous rocks usually cooking it at not very deep temperature, not very deep below the surface. So metamorphic grade is one thing I'd like you to remember. See, there's not a lot of green arrows there before. So you have low-grade metamorphic rocks, you have intermediate metamorphic rocks, and you have high-grade metamorphic rocks. These sometimes are called green schist, amphibolites, and granulites. Rock types included slate, phyllite, schist, gneiss, and over here we have a melt. And so basically, when it's melted, it basically turns into igneous rock again, because it's completely melted, usually by great depth, and becomes igneous rock, and is probably moved around somewhere else in the molten state. These are the minerals often associated with them. So a green schist will have green minerals in it, like chlorite. Whereas the other rocks will be found in higher metamorphism until it's so highly metamorphosed it almost looks like granite. So a important low-grade metamorphic rock will be a chlorite schist. It's lower than this schist, but they're still called schists. This is mostly made of chlorite, as you can see, and is a very useful soft material for making things with, as you might have noticed by now. Serpentine is a low-grade metamorphic mineral and a metamorphic rock. Talc, again a talc schist, is a very useful material and is typically a metamorphic rock, which has been turned into this soft mineral talc. Marble is an intermediate grade metamorphic rock, and so this has completely recrystallized. What was once limestone and may have been like filled with fossils or something like this has turned into large crystals of calcite, which are all intergrown, and so it makes a very nice material for carving. There you go, the hardness of 3. And so this is very popular, of course, amongst the Greeks. The ancient Greeks made a lot of statuary, sculpture out of marble, as did the Romans, using the same thing. In fact, this is an ancient Greek, but it's actually a Roman copy. It's in the ROM. This has led to a lot of problems lately, where people have been talking about the whitewashing of ancient Greek culture, because in Western Europe they often liked to admire the Greeks because they were thought to be more like them. Because after all, if you look at this chap, he looks very Anglo-Saxon, doesn't he? But in fact, he probably looked more like this chap. So this is a bit of a problem. You think that the Greeks would have been outside in the sun all day with a medieval complexion, a Mediterranean complexion, and not as white as some racists might think they were. Another intermediate grade metamorphic rock would, of course, be lapis lazuli. So now we have all the types of rock. That's probably not all the geology I want to teach you, but so we have igneous, metamorphic, sedimentary. Don't forget that above all things, because that's going to be a perfect exam question. Thank you.